and getting too used to it, and I want to stay in my cave. But anyway, hopefully next week we all get to see each other's faces in person. Tonight we are joined by Arun, who is actually did the course last time we ran it, and won, which is pretty awesome in the competition. So he works a lot with recommendation systems these days. So he's going to walk us through this week's content and some of his own learnings. And Huen has also prepared another notebook, which is fantastic. Thank you, Huen. So we'll hand over to them. Please take it away, Arun and Huen.
Yep. Good evening, class. So tonight we welcome Arun from Sydney, and we are very lucky to have him online with us. And funnily enough, Arun and I were actually classmates 4 years ago in the first Fast.ai course, and it's great to have him back, to contribute to spread the knowledge. And there's a lot of material that we are going to cover today, so stay interactive, And if you want to speak, press the raise your hand button and unmute yourself and speak. And first, I'm going to do a little bit of intro into the topic, because as you can remember from Jeremy's lesson, he goes straight into the rating prediction part, and he sort of skims over the context around recommendation systems, which is really interesting in itself. So I'm going to do that brief intro and link it a little bit with our last lesson on ethics before handing over to Arun to go through the details. So the agenda today, we will go through that brief intro and context, and then Arun is going to do the bulk of the lesson with the code walkthrough. He's going to talk a bit more detail about the data block and tabular pandas classes. He's going to introduce us to weights and biases, papers with code, Streamlit, and some of his tips on how to win, the project part of the course. And he will share some useful resources on the topic. And I'm going to cover a bit of a case study on the movie length data set. And we will, in the final 20 minutes of the class, we're going to walk through the exercise that I posted on Discord. So what is the problem that recommendation systems are actually trying to solve? So we live in a world that is inundated with a vast amount of data, and the problem is that it causes us to be unable to find out some useful information, even if we have access to it. Have you ever tried browsing YouTube on a blank slate, or use Bing as a search engine? It's pretty crap. And so basically, recommendation systems were developed to solve this problem of information overload. So if we step back a little bit, what do you think a good recommendation system do? Unmute yourself and speak up if you want to answer the question. What do you think is the goal of a recommendation system?
The goal would be to be exposed to content or products that you would find enjoyable, but wouldn't necessarily have come across on your own naturally.
Yes. Yeah, so it's one of the goals. Does anyone else have any other idea of what a recommendation system should do? So yeah, like Neil said, one of the goals is to be able to predict accurately, what you might enjoy. However, accuracy has been criticized as one of the standard metrics. Elliot, can you please mute yourself? Yeah, so the accuracy of the system has actually been criticized as a metric, because what the system does is that it's good at predicting what you already liked in the past, right? It might not necessarily translate to things that you might enjoy in the future. And about 15 years ago, there was this really famous article called "Being Accurate is Not Enough: How Accuracy Metrics Have Hurt Recommender Systems," which talks about this point. And Ania, our previous lesson mentor, also wrote this wonderful article called "The Wonderful World of Recommender Systems," where he makes the point that having good recommendations is not good enough. Like, you also need to have a good design and user interface so that the users can actually make use of your recommendations. So several metrics have been proposed as the goals for recommendation systems. Things like utility, being to make useful recommendations, serendipity, exposing the users to things that they might not even be aware of, novelty, diversity, introducing them to a wide range of products, and coverage, similar thing. But even if, let's say, even if we have a good recommendation system that can achieve, these goals, what do you think can go wrong? Yep, just raise your hand if you want to answer and unmute yourself. What can go wrong, even if you have a very accurate recommendation system? Crypto, can you speak up? Crypto, can you unmute yourself and speak up?
Well, what could happen is that whilst you might have an accurate recommendation system, you might not get stuff that you haven't seen before or would like to see before.
Yeah, so are you talking about some sort of a filter bubble in a way, like you narrow down your consumption?
Yeah. So you'll only be stuff, for example, maybe you're interested in books on physics, and all it does is offer you on books on physics, but maybe there's some other fields that might be relevant to what you're doing.
Yeah, that's great. And Kamlesh, can you unmute yourself and speak up? Kamlesh?
Hello. Yes, the mute button takes a bit long here. So one of the thing can happen is that if we recommend it directly based on the model itself, it might not be relevant from the business point of view. So for example, you might recommend certain type of shirts or something in a clothing example, in a retail example, to people, but you might not have them in inventory in the size of the customer, and this can lead to a strange problem that people want it, but it's not there. It can create more dissatisfaction than actually creating more satisfaction or something.
Yeah, so there are also some really good answers in the live chat. So maybe irrelevant content, and maybe just the scale of the problem as well, or biases in the model. So at this point, I just kind of want to link back to the previous lesson that we talked about biases and ethics. So even if you have an accurate recommender system, the problem, is one thing to recommend movies, but it's another thing to, talk about like news or medical information. So what happens is what is popular is not necessarily good. And as we have seen in the last few years, there has been a lot of negative press and criticism of these recommendation systems, behind Facebook and YouTube, actually amplifying toxic content and lies and misinformation. So even if we have a good system, the problem is a little bit bigger than that, and we have to deal with, what are the products, what are the things that your system is recommending. So a very controversial topic around recommendation system is around the question of a filter bubble. So the question is, do we get led into a rabbit hole, into a filter bubble where we only get exposed to information that agrees with us? So recall the movie lens data in the notebook. A few years ago, there was actually a very interesting study that looked at these two questions. The first one is, does the system expose the users to narrower content over time, so a filter bubble? And the second question is, do the users taking the recommendations actually have a more enjoyable experience? And I'm going to keep you, in suspense, and we will find out the answer to these two questions towards the end of the class. So stepping back a little bit from the class, there are actually multiple types of recommendation systems. The first one is probably the simplest one, is demographic. So you recommend products or items based on user attributes such as gender, age, nationality. The second type is knowledge based. So you recommend items based on specific knowledge about how certain product features might meet the user preferences. The third one is community-based. So you, based on the user's social network, you recommend things to them that might be relevant. So what do you think are the pros and cons of these different types? Anyone wants to take this question? Neil, it looks like you want to speak up.
Yeah, I was trying to think of the specific one I wanted to start with. For community-based recommendations, that seems to me like it might limit the scope of what a person's exposed to, particularly if one is in a more culturally isolated environment. It will keep them from being exposed to things that are outside. It's like only trying chocolate or vanilla ice cream when there's 1,000 other more fascinating flavors out there.
Yeah, so I mean, these different systems have their own, problems. For example, demographic can be a little bit coarse, like just dividing people by gender or age or nationality. You might not capture all the interesting things about their preferences. Or knowledge base requires specific domain knowledge. Another type is based on content. So basically, it's only based on the attributes of the item. So every product or every item has certain features or attributes, and based on what you have liked in the past, the system can recommend you things with the same or similar attributes that you were looking for, and it works well. But the problem is that it requires you to have these descriptive data about the product, and who is to say what is relevant, right? Like if you have a new movie, how do you know what features are relevant to the user? And the next type is collaborative filtering, which is the main, the bulk of this lesson that Arun is going to go into detail. And it's basically makes suggestions based on how similar users rated in the past, and not based on the product themselves. So let's say I go on Amazon. Amazon will look at people similar to me. What have they liked in the past? What have they bought in the past? And recommend those products to me. But the question here is, how do we measure similarity? So let's say if we have a user to product matrix like this, can we treat each user as a vector of all their ratings, and just simply say calculate the coefficient, the correlation coefficients, between them as a measure of similarity? What can go wrong with that approach? What is the problem? Can we represent user 1 as a vector of 4, 3, 2, 5, and user 2 as this vector, and maybe just calculate the correlation between them to find out how similar they are? Is that a viable solution? So the answer, Michael's answer is only if you have enough info from each user. Can you clarify your question, your answer, Michael?
Yes.
Yeah.
Sorry, I was just unmuting myself. So obviously, if you've got information for each user about the sorts of movies they like, then that works. But if you've never seen that user before, how do you know which ones they're similar to?
Yeah, so let's just say that we don't have the new user problem here. So that problem that Michael was talking about is called the cold start problem. So when you have a new user, you know nothing about their preference. But let's say all of our users have used the platform for a while. What can go wrong with this approach? So somebody said they might have different weighting. Can you speak up? Why? What do you mean by that?
Yeah, by that I just meant we might have like a certain bias, if you want to call it that, applied to each of the users. So say one user might just be more of a critic of certain movies versus another. Like one might give an average weighting of 5 versus the other that might give an average weighting of say like 3 or something.
Yeah, but I mean, let's just say that all of the ratings are reliable. Can we use this approach?
Yeah, well, like I'm just saying that, if someone has an average rating of 3 and then they give it a rating of 5 for one movie, but you're comparing that directly to another user who has given a rating of 5 to every movie, then you're not really like taking into account that difference there.
Yeah, so actually, non-rated movies. Okay, Moji, can you speak up? What do you mean by that?
So, can you hear me?
Yes, yeah.
Yes. I thought that maybe user 1 doesn't have a recommendation for movie number 10, for example, but user 2 has it. We need at least to find a way to either exclude those parts if you're doing vectors, or if there are a lot of them missing, then this wouldn't.
Yeah, so I think we're getting towards the right answer here, and Mario on the chat as well. So the problem here is that we have a very sparse data set, right? The real life is not like this. We might have millions of users and millions of movies, and most of the user to movie rating combinations do not exist. Most people have not seen most of the movies, and most of the movies have not been seen by the users. So that means that if you represent, a movie or a user as a vector, most of the entries are 0, and so it's a very sparse, vector, and that is very problematic. So, and that's why we use embeddings as a dimensionality reduction technique. So instead of representing a user as a vector of a million, numbers, most of which are 0, we represent them by a vector of say 50 factors, and that will massively reduce the problem, the computation and the accuracy of our model. So next I'm going to hand over to Arun to walk us through the details of what happens behind the scene. Over to you, Arun.
Yep. Can I please share my screen? One second. I'm trying to move this screen to the screen. Yep. Can you all see my screen now?
Yes.
So I'm turning on my video. Okay. So in today's class, what we are going to see is we are going to use some datasets. So in one of the dataset, most popular dataset is movie lens. So we'll be using movie lens, and we will understand how to clean those datasets to build some models, and what are the different kinds of models we can build to recommend some products to some users, and what loss functions can we use to optimize the entire flow. So I will start with some dataset first. So we will be using this movie lens dataset. So this dataset has lots of users and lots of movies and some ratings. So I'm using pandas pivot table to display like this. You can see users arranged from 1 to 943 and movies arranged from 1 to I think 1682. And like as Rin said, most of the users don't watch a lot of movies, so it should be lots of zeros. We'll figure it out how to solve this problem. So before talking about the model building, let's talk some about the intuition behind these collaborative filtering models. So let's say I'm going to represent two things. One is some of the books, and another thing is student. So let's say this is fast AI book, and I'm going to represent this fast AI book with some 5 different numbers, range from -1 to 1. So it can be any number between -1 to 1. Maybe those 5 things are like whether this book is practical or theory oriented, whether this book is recent or old book, whether this book uses Python or not, whether this book uses PyTorch, and how expensive is this book. So if it's practical means I'll assign some high number. If it's less practical means I'll assign some negative number. So that's the goal. So let's use those things to assign first A book. First A is practical, so I assign some positive number, so which is a recent book. Then it uses Python, PyTorch, and it's less expensive and it's open source. So I'm assigning some negative number here. For the same thing for PyTorch book, this is deep learning, introduction to deep learning with PyTorch. So it's a great book, very similar to if you are reading Fast AI book. I think I highly recommend you to read this book too. And this book is highly practical. They use some medical image datasets, and this is recent. It published on 2020. And this book uses Python, and it's purely PyTorch based, and it's less expensive. Also, it's open source. Then another book, Statistical Learning, which is very old book, published in 2009, I guess. And this is mostly theory oriented, which is not a recent book. Then this book uses R programming, not Python. Then this book doesn't use any PyTorch, and it's a little bit expensive. So I have represent each book with some numbers. Then let's say there are 2 students, student 1 and student 2. This student likes to read. This is his expectations. He likes to read a practical book. He likes to read recent book. This is his taste. So now let's try to match his taste with some books. For example, student 1 with first A book, it's getting like 3.09, which is just a dot product. What I'm doing is I'm multiplying 0.9 with 0.8, 0.8 with 0.85. Likewise, I multiply with everything, and then I take a sum, which is very similar to nb dot student 1 fast AI book dot sum. So I'll be getting this number. Then let's try to find this student's taste for PyTorch book. He's getting some positive number. Now this student's taste with statistical learning, he's getting negative number, because those student 1 and statistical learning are very opposite taste. So in this case, we can recommend fast AI book and PyTorch book to him, not statistical learning book. And another student who likes to read old books or programming books, those kind of things, for his taste, we can recommend statistical learning book, not these 2 books. So this is like a intuition of latent factors. So this, one second. So usually these numbers, like we used numbers between, we used like 5 numbers. So normally we can play with this. So we can use 50 different numbers. So usually we don't know what each number means. Here I just used, you can see it here. Here I assigned practical, recent, Python, PyTorch, expensive. But if it's like 50 factors, we don't know what each factor means. That's why it's called latent factors. So how do we get this number? So there are, let's say I'm using 5 different numbers. So here we use some simple data set like book, and these books are fast AI, PyTorch, and statistical learning. We know about those books. We can come up with some numbers. Let's say you're working for some retail. There are millions of data sets and millions of users. In that case, you can't create these embeddings by yourself. What you could do is you can assign some random numbers, any numbers between up to you, like -2, -1. It's just a random number. Then what you can do is you can treat each random number as a weight. You can train a model. For example, let's say we have some user and some movie. In that case, we built a dot product, which is user multiplied by movie and then sum. That's a dot product. For each embedding, if you do that, you will get some number between, let's say you are getting number between 1 to 5. So this is your prediction. And then what you can do is you can compare this prediction with the real truth. In movie lens dataset, the real truth is like a rating 1 to 5. Let's say our model predicts 3 and the real output is 5. In that case, the error is like mean square error 4. So what you can do is initially those user embeddings and movie embeddings or random numbers, and then it updates itself based on this mean square error. If you try to optimize this model, those embeddings will be meaningful at the end. So before we know about latent factors, let's talk about the embeddings. So embeddings are nothing but just a fancy way of saying take some data from some array, that's all. So let's say we have user 1 to 50. So there are 50 users. You can create some array lookup like 0 up to 50. Each user has some random numbers. If I ask you what's the embedding matrix size, you can say there are 50 users and 50 numbers. So this is the size of this embedding matrix. And if I ask you what's the embedding matrix of user 0, you will return this matrix. It's just a fancier way of saying lookup. So let's go through some of the code and we'll see some intuitions behind each things. Here what we are doing is we are merging the title with the rating datasets. And then there are so many ways to create some data loaders. We'll go through some of the data loading techniques, and then we'll jump into these modeling techniques. So let's focus on data block and tabular pandas. So why I'm going to use tabular pandas and Collab data loaders is the difference between some collaborative model and some tabular data is nothing but in collaborative modeling, you'll be using just categorical features. But in tabular datasets, you could use both categorical and continuous. That's the only difference. Fast.ai uses tabular pandas behind those collaborative filtering models. So I'll start with this blog post. Quickly skim. So this blog post is a great way of introducing to data block API. So what is data block API? Why should we use data block API? And what are the things we can customize in data block APIs? So first of all, why should we use data block API? Because data comes from different sources. So there are so many sources. So data block API is one of the best way of getting different data from many sources and make it in a meaningful way to the model that understands. For example, let's say you have lots of images and maybe the output is like cat or dog. In that case, we need to convert those images to some numbers so that models can understand. And also you'll be doing lots of different splits like training, test, and validation splits. And this data block API takes care of those things. You no need to write lots and lots of PyTorch code to manipulate this data so that model could build some meaningful models. So this data block API has 3 different main things. One is getters, how to get the raw data set, from where to get those raw data sets. Maybe this is file path or some pandas data frames, and how to transform those data sets so that some models can understand some data, and how to split the data sets into training and validation data sets, those kind of things. So this is, if you see this code, so this is like a structure or framework. So if you see this, we are going to use some image block and category block because our input is image and our output is some label. And how to get the image? So get the image from some files. how to split the data, randomly split 80 or 20, 80 for training and 20 for testing, and how to get Y, which is the label. You can get the label from the file name. And what are the transformations you can do? One is item transformations. So item transformations applies for each file before putting anything to the GPU. And in batch transformations, for each batch, you do lots of transformations and then you put everything to GPU. So this is like a structure. We didn't say anything about where to find the data. So that's what we can say to the data loaders here. So we just initialized pets as a data block framework or structure. And then you can use this image folder to do these things. So here's a data block. And then we are telling them you have to use this file to split and get all these things. So getting, splitting, and how to find the X and Y, those kind of things are here. So I think there are three different things. One is low-level API, mid-level API, and then high-level API. The high-level API is like a factory methods. Maybe the CNN learner, those kind of things are like high-level. And this is like mid-level. So most people, I think I saw one of the tweet on Twitter about what's the most recommended things to do with low, medium, or high. I think most people voted for mid-level API. This is data block. So this dataset and data loaders are very similar to PyTorch. So if you're dealing with some different or some unique way of dealing some datasets, in that case, you can use some low-level API directly with datasets and data loaders, and then you can merge everything with learner objects. So I shared this presentation on in today's presentation. Also, I highly recommend going through this one, as well as two more videos. One from Vishnu. This is building fast.ai data block step by step from scratch. And also he has two more videos. You can go through it. So now let's talk about this one. So if you see, so we know about data block API, but if you're trying to use data block API for some Collab filtering, you can't do that because Collab filtering uses different kind of API. One is tabular Collab and Collab data loaders. So in Collab data loaders, you can use directly from data frames and also from CSV. So now let's jump to coding. So instead of using data block API, we are going to use some high-level Collab data loaders. So we have already built a ratings data frame. So that's why we are going to use this Collab data loaders from data frame. So what are the things we can do is we can directly pass the data frame and how to get the item name. I think the default is item, and sorry, the default is name. Here we are using title. So that's why we are using item name as title. And batch size we set as 64. We can play with this. So as I said before, these embeddings are just some random numbers. So let's say we are using some 5 different latent factors. In that case, you randomly create some numbers for each user, create some 5 different random numbers. So here what we are going to do is we are building some models. So now you know how to convert some data sets to way to deal with modeling. I think we are heavily focusing on these things, Collab data loaders and tabular pandas and few other things. And also at the end, I can show you what are the things Collab data loaders use behind the scheme. Okay, so in our case, we are using number of factors as 50. So in my example, I used 5, but here we are using 50 latent factors. And initially, those different latent factors are some random numbers. And we are using mean square error loss function. Then we are going to deal the model building. So initially, those numbers are random. And after some training, those numbers should be very meaningful. I think in the fast.ai book, Jeremy did lots of visualization to understand how the embeddings looks like in 2-dimensional space after using some PCA. So do you have any questions on how to train a model? I think I'm just going through some of the messages. So one of the question from Leo is, can you load 2 data sources into a common data loader? Yes, we can. And also we can use different types. For example, one of the, at the end, some of the things are like, you can sheet. Yep. He used different sources, image block, which is input, and in the output is like bounding box and the label. To mention these things, you have to use number of inputs. And also to know more about some of the splitters, so I just read some question about the index splitting. You can use this website. So I'll share this. So if you want to quickly understand how to train some modeling, so actually I run a meetup group with Tim and Annie. We usually start with some basic example like this. So let's say I think I can quickly go through it. So it builds some strong intuition about model training, as well as why should we use some non-linearity in between the models. I can quickly go through these things. For example, let's say there is a data set like X data and Y data. So let's say this is like number of hours you study, and this is like how many marks do you get after some hours of training. So in that case, you just multiply X and W. Initially, you assign some random W, and then based on some model training, you can get some good W at the end. So your loss is like mean square error, which is like just output minus the prediction whole square and take all the sum. So if you see this problem, you can say the W should be 2, which is very perfect. But computers don't understand that way. It randomly starts with some random number, and then based on the feedback, it trains itself, and at the end, you will get some better numbers at the end. So let's say you're using W equal to 0, what's the loss? You'll be getting 18.6. And if you increase W, you can see some losses going on. And when W equal to 2, you're getting perfect model. Because this data, if you see this data set, you can easily say W should be 2. That gives the best result. So this curve looks like this. And what you can do is you can find some gradient for each point. For example, let's say you are here. If I increase W a little bit, my loss going to increase. But if I'm here, if I increase my W a little bit, my loss going to decrease. So I can directly do some gradient descent update here. So here our problem is very simple. We can find gradient by ourselves. But when you are dealing with 50 latent factors and millions of data points, in that case, you can't take derivative for all yourself. So that's why we are going to use some libraries like fast.ai or PyTorch. Then after some training, so this is the initial model. Initially, the loss is like 2.4. After some training, you're getting loss very close to 0. And our model W is 1.9. So which is very close to 2. And I'm going to show you one more thing about some intuition behind why should we use some activation functions. Let's say, so this is important because one of the tasks is to use Collab neural network. So let's say you are using some different layers. So initially one weight is 2 and another weight is 2 and here another 2, another 2. Let's say you are not using any non-linearity in between these layers. So what you can do is you multiply everything like 2 multiply by 2 and then at the end you put it to another 2 multiply another 2, you will get 16 at the end. So there are no non-linearity in between those two layers. So if there is no non-linearity between these two layers, what you can do is instead of building two different layers, you can directly assign weight as 8 multiplied by 2 in a single layer. You can play with these weights without using other layers. So this non-linearity is very useful because it can learn any function. So that's called uniform. So universal approximation theorem. I can quickly go through those things. So here, some of the activation functions. So this graph is very important. So this is maybe this is one layer's curve looks like this, and another layer B. If you combine these two things, you will learn some functions like this. So tan H, it looks like this. Another activation functions with different weights, it's here. But if you combine these two things, you can learn some functions like this. And also if you combine many different layers, you can learn any different functions. I think it builds some intuition on why should we use some non-linearity in between the layers. So one reason is if you don't use any non-linearity, a single layer can learn those weights by itself. So instead of using 2 multiplied by 2 and again 2 multiplied by 2, you can directly use a single layer with 8 multiplied by 2. So if you use some non-linearity, it learns some complex patterns between one layer to the other layer. So that's some little bit intuition behind those things. So now let's move to our coding. So initially I said these embeddings are random numbers. I'm going to ask you one question. So let's say the embedding size is 50 and we have number of users. One second. Okay, so we have 944 users and we have 1665 movies with the different latent factors. Can you tell me what's the number of parameters in this model? You can unmute yourself and talk. So 50 is wrong. Then we are using latent factors as 50, but we have 944 unique users and 1665 unique movies. And for each movie and for each users, we are assigning some 50 different numbers. And then during model training, we are going to learn each number. I think Neil is correct. So if you can use learn.summary function in this object, it tells you how many unique parameters in this model. So we have 943 users, and then, but Neil said 944. I think additional one number is for some different users not in the dataset. So 944 multiplied by 50 latent factors, you will get 47200, which is here. And then we have unique movie 1682, but we are adding one more number to find some new user, sorry, new movie. In that case, 1683 multiplied by 50, you'll be getting this number. And then again, you are going to add bias for movie, which is 166. Sorry, in this case 1682, and for users case it's 944. So I hope you understand the basic dot product model. So this is a basic dot product model. So what it's going to do is, there are around 900 users and around 1600 movies. For each user, it assigns 50 random numbers, and for each movie, it assigns 15 random number. And then during training, it updates those random numbers to reduce the loss. So in that case, we built a model which is a dot product, and then we are going to build a learner object. So in this learner method function, you can pass the data loaders and model, and we are going to use mean square error as a loss function. Then I'm going to train this model, so it's improving. So what else we can do to improve this model? One thing is setting this Y range. So what it does is, we already know this is a movie rating. In movie rating, the output is like 1 to 5. So the range, we are setting the range as 0 to 5.5. So let's say your model says 10 or 15. It doesn't make any sense. It's a huge number. So in that case, you can reduce those 10 or 15 to between in this range. So this is sigmoid range function. It converts any number to those ranges. So far what we have done is, we just created some embeddings, but we didn't add any bias. So how about adding some bias to each users and also for each movie? For example, some person likes to watch some particular type of movies. He always assign some high rating for some particular type of movies. So in that case, we can just add some bias for him. So once you add some bias, let's see whether the model improves or not. In that case, it's not much. It's almost the same. And another intuition is, we are going to use weight decay. So what is weight decay? The main intuition is like, let's say you have 4 neurons. Once again. Yep. So instead of creating everything to one neuron,
Actually, Arun, we covered weight decay last week. So
Okay.
maybe
Yep,
can
cool.
anyone in the class maybe answer, what weight decay is? Let's see if you remember from the last lesson. Can anyone remind the class what weight decay is? Mochi? Yep.
What we add to the loss function to limit the values of weights.
Yep, correct.
Yep, yes, that's good. So we should not use some high weights. So in that case, you can distribute the weight. Okay, so one of the questions from Utsav is, does Y range clip the final results or does it clip the labels before training? So our label is like 1 to 5. So movie rating between 1 to 5, but our output can be any number. For example, let's say you are doing some dot product, you may get numbers like 15 or 25. In that case, we can clip that number to 1 to 5. So to answer the question, Y range clip the final results, not the label. Okay, so far what we have done is we have directly created some model and then we used a learner and you put the model to there and it's working. But you could also use Collab Learner function. In that case, in Collab Learner, you can pass just the data loaders, and then you can tell how many factors you want. Let's say, for example, for movie, you want 50, and for user, you want 20. In that case, you can use some tuple, and you can pass some Y range. So in that case, model training going on, you are using some weight decay. So here, what we are going to do is we are trying to interpret some of the results. So after some training, I said, and also Hyun said, those numbers should be very meaningful. So before training, it's a random number, but after training, those numbers should be very meaningful. You can collect all the weights like this. So learn.model, it has I weight, and you can collect. So this I weight is like a embedding. You can get the weights from this embedding. So this is like NumPy. And then you can find some index for some title. We already use title in our datasets, not for modeling, but for our understanding. Then you can use any distance metric to find closest distance between this movie with all other movies. So this is one way of recommending some products. So earlier we talked about PyTorch book, fast.ai book, based on some taste. We are using similar things here. For that movie, these are some of the movies that's very similar taste. It may or may not perfect. So far what we have seen is, I think I'll quickly finish because we are going to focus on exercise. Before that, so far we have covered what is embeddings, dot product with bias. Now let's talk about Collab neural network. So Collab neural network is nothing but just combining all our users and movies as a single list, or maybe it's single layer, and then add some non-linearity in between. So we already know why should we use some non-linearity. It's very useful because it can learn any complex functions. We are going to use the same approach here. So what we are going to do is, here this is user factors and item factors. And then in a sequential model, we are combining everything as a linear layer. And then we add some non-linearity in between those linear layers. And we can use still the same Y range and other things. And we are going to train our model. In this case, we didn't get any better results. Maybe after some weight decay, we are getting some results. So instead of writing these code by yourself, what you can do is you can directly use Collab Learner. In that case, you can say use neural network. if you use, say, use neural network equal to true, it combines both user and movie as a single layer, and then it adds non-linearity in between. You can say how many layers you want, those kind of things. Okay, so far we have got some good understanding of different things. Maybe I'll quickly skip. So now let's talk about weights and bias and few other tools that's very useful for your modeling and some of the work you do at work. Okay, so here I'm using weights and bias. So before that, I'm going to answer Leo's question. You will still need to match the size of each source. Yes, that's right. We need to match the size between number of neurons and the number of layers so that you can do some matrix multiplications. Okay, so weights and bias is one of the way to track our experiments. So you can, if you're using fast.ai, you can directly use weights and bias. So it's just a few lines of code. So you can go through weights and bias website by yourself. Here I'm quickly showing you some of the things from their documentations. So we can create some callback, and you can pass the callback in both learner and also during training, so that it tracks all the details about your model training, and then you can visualize your results. For example, this is the loss of the entire model training, and for each layers and for each weights, you can see the gradient, how gradient flows. Actually, this is less useful for collaborative filtering, but for different models like image or audio or video, it should be very useful, because you will be dealing mostly with number of layers and debugging and trying with different approach. Here, some of our model results. The true rating is 4. Our model predicts 3.3. For 5, it predicts 4. This is pretty good. I think I'll finish this in 5 minutes so that you have some time to go through the exercise. So where to get more code and more data sets and more approaches? You can use Papers with Code. So this is Papers with Code website. Zoom a little bit. So you can see what are the different approaches for dealing with those recommendation systems. So collaborative filtering with deep learning is one of the subset of so many techniques. So let's say if you are working for some retail industry or different industry, in that case, you will never know the user's details until he purchases something. For example, if I'm going to some Amazon website, I can add so many details to my bucket, and at the end I can sign in and do some purchase. So I'll be doing sign in only at the end. So before that there is no user information. So in that case you can use some sessions, like how I am clicking, those kind of things, how I am navigating, what are the details I'm looking. So you can use those sessions to train some models. So there are so many different approaches. So let's say you want to use this approach, you just click the code and you can go through some of the paper. And if you're going to directly use some GPU, what you can do is you can use this library, Collab Code. It's from Abhishek, which is one of the grandmaster. Just a few lines of code, you can directly click and open a VS Code. In that case, you can use GPU, and also you can do the same thing with Kaggle. If you are doing the same thing with Kaggle, you can access all the datasets on your VS Code root directory, which is pretty good. Okay, so I covered a little bit of Papers with Code. So next one is...
Maybe you can move on to the tips on the projects, maybe?
Yep, sure.
In the interest of time.
Yep, I'll finish in 2 minutes. So one is Streamlit. You can just quickly go through the Streamlit. So Streamlit is a best way of creating some demo for your models without using any HTML or CSS or JavaScript. It's purely Python focused. You can use Streamlit to develop some visualizations. So I'm going to give you some tips on the projects. So I participated in the same fast.ai course in 2017, and I won first prize, as well as I won few other competitions in Brisbane, as well as in overseas. So some of my main tips is just instead of showing some results, always show some demo. And if you are going to also showing demo is one best way of doing or getting some winning. And another is instead of using some data sets from Kaggle, maybe you try with some real, you can collect your real data, different problems, real life problems. For example, let's say in some, you want to analyze some product. In that case, you can collect you can scrap some websites and learn all those details about the product. And maybe you can build some summarizer or maybe sentiment analysis, those kind of things. What I'm going to say is build some end-to-end solutions, right from data, build models, do lots of visualizations, exploratory data analysis, then build demo. The demo, if you have a good team size, it's good to build, it's good to build some front end as well as some serverless backend or different architectures. And my main thing is build some demo. I think in all the previous hackathons, what differentiate myself and some of my fellow teammates is I always took some time to build some demo so that I can talk to the judges. And because sometimes judges don't understand some numbers. For example, for a data set, if you say I got root mean square error as 0.2, it's very hard to get some context in less time because they'll be spending 5 to 10 minutes on a solution. So if you show some demo and if you go through some examples on live, they will quickly connect with you. So that's one of the best approach. So I always recommend you to do some demos. But if you're going to use some demos, you can use Streamlit. So in 2017 and 2018, I was mainly using Flask and some HTML, CSS. But nowadays it's very simple. You can quickly build a demo in few lines of code, and then you can deploy, and that's all. I think due to the time limit, I'm going to hand over to Hyun. Thanks, everyone.
Thank you, Arun. Any questions for Arun?
Moji has a question.
Yeah, I was gonna ask, apart from neural network, what other algorithm people may use? Is it like something like XGBoost? Is it?
For product recommendations?
Yep.
Yeah, if you have lots of different kind of data, you can definitely use XGBoost kind of models. Actually, I can quickly share some of the blog posts that Jeremy has written previously. He has written some books on data products. I can quickly go through it because a recommendation system is how you approach the problem, not the collaborative filtering approach or different approach. You can definitely use XGBoost and different kind of models for product recommendations.
Yes, thanks.
Cool. Thank you, Arun. Okay.
Well, I was just going to add to that. I think one thing to note with recommendation is that I put a comment in chat just before about there's certain challenges like the cold start problem, and yeah, essentially with recommendation, you're trying to use it's kind of a recurrent problem, right? Because you've got a series of previous interactions that someone has had with, for example, books on Amazon, and you're trying to predict what happens next. So one of the things to solve with these approaches is essentially to keep a representation of current state with the model. So something like collaborative filtering will weight all of the different interactions by default as the same. So, you know, a book that you might have read 10 years ago will get, if you rated that 5 stars and you rate a book these days with 5 stars, what you find is that the model will essentially treat them the same with collaborative filtering. So one of the reasons why you would move to some of these deeper models, and I guess the latest methods, collaborative filtering's a very old method these days. A lot of the newer methods essentially come up with a representation of these items that sort of updates as the user makes new decisions. So Definitely worth checking out some of the other research in the field if you are interested in this, particularly if you're interested in how this works at scale, because it's really challenging to actually do this at scale, make a prediction for every single item. And what a lot of the companies actually do is that for something like Google or whatever, they might pick the 1,000 like best candidates with a really fast method. And then they'll run recommendations on the top 1,000 that they picked and then re-rank those. So it's like select the candidates and then re-rank. It's quite interesting. There's a lot of engineering challenges with this sort of stuff. So if you're interested in this, definitely check out some of the links that I shared from Eugene Yen, which sort of talks about not only different methods in personalization, but also how you actually put these into production and into a product. It's quite interesting.
Great, thank you, Michael. Can you post these links on Discord so that people can check them out?
I can, I'll drop them in there as well. Sounds good.
Great. Okay, so now we're going back to that case study that I mentioned at the beginning of class. What do people predict the answer should be? Do you think that MovieLens recommender system actually led people to narrower choices over time? Anyone wants to hazard a guess? Ranjan?
So if the user stops interacting with the system, then maybe over time, the system will only work with whatever data it had on the user before. So over time, if the user stops interacting, the recommendations could get narrower and narrower.
Okay, so your prediction is that it does get narrower over time. Does anyone else want to make another guess? Yeah, okay, so we can quickly go to the answer in the paper, and it's actually really surprising and interesting. So what they found is that yes, the people that do take the recommendations do actually narrow their movie consumption over time. But the people who did not take the recommendations narrow their consumption even more. And that's very surprising, right? I mean, what we see at the beginning here is kind of expected, over time as the system learns more and more about your taste, it will sort of narrow down, what you enjoy, and it will narrow down the recommendations. But what is surprising is that that also happens to other people who don't actually interact with the recommendations. And the reasons for that, they think, is that as people watch more and more movies, they do get to know their taste better, so their consumption becomes naturally narrower over time. And after a while, people just run out of good movies to watch. So over time, everyone narrows down their consumption, but actually the recommendation system lessened the risk of a filter bubble. And I found that very surprising and very interesting. About the comparison between taking versus ignoring recommendations, the authors of the paper found that overall our users watch less enjoyable movies over time. And isn't that very surprising, right? You think people are on this platform, they should be able to find better movies, right? But this is a classic case of Simpson's paradox. So there are actually two subgroups of people: the following group, who do take the recommendations, and the ignoring group, who just ignore the recommendations. So the following group actually enjoy the movies the same over time, and they did like the recommended movies better than the non-recommended ones. The ignoring group enjoyment actually went down, and the reason for that is probably because of the reason I mentioned before. They just ran out of good movies to watch. And so overall, this group that ignored the recommendations did the worst. So they did watch significantly less enjoyable movies over time. And so towards the end of the paper, the authors actually make several recommendations for a good recommendation system. And so basically they say, it depends on how you build your algorithm, but you should build it so that it can slow down this process of narrowing effect that naturally happens over time. And secondly, you should inform the users about the diversity of their consumption, alerting them to the fact that, hey, maybe you are going down a rabbit hole. And there might be these new things that you can check out. And finally, they say, if even after you've done these things, it's still not enough, to reduce this, filter bubble effect, this narrowing effect, then maybe we should intentionally increase the diversification, of the recommendations, to counter these effects. So yeah, I highly recommend that you check out this paper, and I just leave it with you as a food for thought. So next we are going to go through the exercise that I posted, and I thought, just for fun, I thought maybe we can do something like this. So I'm going to share a file, and what I will ask you to do, and it will be interesting to see how this works, is basically you can enter your own rating data here. So let's do this as a class exercise where you can put in your name across these cells, and then you can put down the ratings, and you don't have to fill up everything. And then we will use this real data to build our recommender system. And yeah, and then let's see, how good our model actually is. So that's the link to the file, and I will also share with you the link to the exercise, and we can go through the exercise together. So once you have filled your data in this spreadsheet, then just start looking at so the rating is out of 5, from 1 to 5. So 1 is the lowest and 5 is the highest. And then once we have filled up the data, then we will actually use this real data to build our system. You don't need to fill up everything. You can leave some blanks so that we can do predictions. And let's see how good is our model. Cool, we actually have quite a lot of people already. So maybe in the interest of time, we stop at the letter Z. Once we filled up to that column, then we will stop collecting the data. Stan, I see you jumping around from one cell to another.
Yeah, they keep stealing my spots. Too slow.
Okay, let's give this another minute, and then we will stop collecting the data, okay? Okay, so column AB with Stan will be the last column. So if you haven't entered the data, please do not. Josh, you have the whole column, a whole empty column to yourself, column W. You still want to fill up the data?
Yeah, actually it's supposed to be full.
Okay, I don't see anything on my side yet.
Let me try again. Sorry.
Yeah, so for people who have completed entering the data, I have posted a link to the exercise notebook. So you can start exploring, you can start looking at the exercise notebook and start thinking about the questions. Okay, great. So maybe let's stop downloading. I mean, let's stop entering the data from here. Okay, yep. Let's freeze it. So Sean, I saw that you, okay, the scale is from 1 to 5. You got 101 and -5. Stephen is cheating. Yep. Okay, so now that's the data, and you can start downloading this data. And so I will start downloading the data now. And you can use this data in your Collab notebook. So the way you do it is really simple. You just open this button here, and that will show you the files. And you can just drag the hobbies Excel file in there, and you can start playing with the notebook. Oh, when you say you got the permission issue, is that okay? Sorry, yep, let me see. Permission. I really enjoy how easy it is to extract information out of people. You are very trusting. Can you check that you can open the Collab notebook? Great. Cool. Yeah, so you just download that Excel file and you can just drag it into files. So click on this button here. So I will give you about 5 minutes to skim through the notebook itself. And then we'll get back together and go through the notebook in 5 minutes. So Owen, just download the Hobbies Excel file to your computer and then drag it onto Collab, and we will use hobbies.xlsx to download.
Gotcha. Cheers.
Does anyone have any issue with running the code using that Excel file? Just shout out if you have any problem. So Peter, I just posted a link to that Excel file, and you can just go to File, Download, and it will download to your computer. Yeah, so in the interest of time, maybe just skim through the notebook and read all the questions, and we will go through it together shortly. Cool. So maybe we will start going through the notebook together, and so be ready to answer questions. Yep. So I'm just running the first few cells to load the data here. So we have the ratings data frame in this nice format here. So the Collab data loaders class sort of assumes that the first column is the user and the second is the item. And I have been too lazy to rewrite this notebook. Yeah, so just treat movie as hobby. Yeah. Okay, so can anyone fill in this code here? How do we complete this Collab data loaders line? Actually, we want to use title. Hobby. Anyone wants to type in? Yep, but also we want to have a batch size of 10 as well. So how do we specify the batch size? Great, yep, Mario has got the right answer. So I'm just going to copy paste what you have. Yeah. Yep, so that works. So we got the data in the data loaders. Maybe we will skim through this. So how sparse is this matrix? So basically, what is the number of ratings divided by all the possible user and movie and hobby combinations? Can we, Mario, can you type out the code to get to the answer? So you have CT shape 1. So what CT? Okay, cool. Yep. Yeah, so our data is actually not very sparse. So it's 90% full. Whereas if you go back to the movie length data, then it's actually 94% empty. Yep, so this is Mario's answer. So we got, yeah, 90% full. Okay, so these steps here defines the model and creates the embedding matrices. Can someone explain what is happening in the forward loop, in the forward pass? Can someone unmute themselves to answer this question? Does anyone want to take a stab at this question? Yeah, Mario?
We're doing the dot multiplication. First take the users, then you take the movies, you multiply them, and then you add it up. Yeah, then from there, I'm not quite sure.
Yeah, okay, so maybe I can help you out. So X is basically our ratings data frame, right? So in each row, you have user as your first, the user index is the first column, right? And the second column is the item. So basically what you're doing here is you are looking up, you're doing basically a VLOOKUP in this user factors matrix, right? So this term here is the index of the user. So you're looking up in this matrix, what is the embedding? What is the vector for that user? And this term here is the movie, is the ID of the movie. So you're looking up in this movie factors embedding matrix, what is the vector for that particular movie? And once you have the vector for that particular user and that particular movie, you do a dot product together, right? So that's what's happening here. And then you also want to add the user bias term and the movie bias term. And you want to force this output into a range from 0 to 5 or 5.5. And that's why you have this final step here. Does that make sense? Does anyone have any question about that? Yeah, it took me a little bit of time to understand that step as well. What is the meaning of this Y range? And why do we want that constraint?
The Y range limits the output of the function between the first value and the second value, so that it can't produce outputs that exceed the bounds of the problem statement.
Yeah, that's great. So remember that our ratings are only within 0 to 5, and that's why we want to limit, we want to constrain the output of our model to be within the same range. The next question is interesting. Why do we use MSE loss as the loss function instead of cross entropy? So Elliot, I saw you raise your hand before. Do you want to take this question?
That was actually for the last question that I raised my hand.
Do you want to try this one?
I don't have any idea, so I'll happily yield the floor to someone that does.
Okay. Anyone else apart from Neil before he takes the floor? Mario? Yep.
MSE is regression. So you're trying to get as close to a number where the other loss, cross entropy, is more categorical.
Yeah. So, yep. So I'm going to, so this, remember that we are doing a regression problem, but what do you think is the problem with that for this particular problem? Neil?
We need a distance metric between the space between the value that you're attempting to predict and the value that is predicted.
Yeah, so I understand that, but even if this is a regression problem, it's a little bit more subtle than that. So think about our ratings, right? They are 1, 2, 3, 4, 5, right? They are not just any continuous number. Correct, right? They can't be 4.37. But there's nothing in our model that is constraining that. There's nothing in this forward pass that is forcing the output to be discrete numbers, right? So this is actually called an ordinal regression problem. What it means is that your output is actually not a continuous number. It's actually, they are ordinal. So they have fixed values, but they do have an order to it. Yep. Does anyone have any question about that? And why, and what would be a problem with using the cross entropy? Let's say if we treat this problem as a classification problem, and we try to classify between 1 and 5, what would be a problem with that? Neil? Yep.
So while each are discrete values and they're not equidistant from one another, there is understanding that a 3 is greater than a 2, and so on and so forth. Yeah. However, there's an interesting way that you can implement cross entropy for this problem. Instead of using one-hot encoding for the value, you can use a technique called binning, where instead of changing value to be a vector that has zeros for all the non-correct entries and 1 for the correct one, you have a vector where, for instance, a value of 3 would be represented as 1, 1, 1, 0, 0, and so forth, and then you sum it to get the actual.
Okay. And how you change the loss function then? Is that still a cross entropy loss function?
You can still use cross entropy loss with that, or BC loss logits.
Okay. I mean, I would love for you to actually implement that and share it with the rest of the class, because yeah, that's new to me as well. And let's see if it actually works. Yeah.
I'll send a couple of links. I used that in a competition last year with fast AI.
Great, excellent. Cool. So going down, so we're going to define our model. Oops. Okay, so we need to fill in these question marks. Does anyone want to try this? So in this case here, you are initializing the model. So you're initializing your embedding matrices. So can you show us the dimensions of these matrices? Yep, great. Okay, so Mario has got the right answer here. So I'm just gonna copy and paste this code. Yep, so for the embedding matrix, so we have n users as the number of rows, and then n factors as the number of columns, right? So each user is represented by a vector of n factors. Yeah, and then we also have these user bias terms. Yep, so we can define that. It's still complaining. So we have 28 people in the poll. Can anyone fill in this line here? So we have defined our model. Now we need to initialize it. Yeah, I'm not exactly sure why the range that Jeremy chose was between 0 and 5.5, because I think all of the ratings are between 1 and 5. But let's check our data, because I think Mac, somebody actually ruined our data and entered 10. Okay, so I think I'm just going to make the range between 0 and 10. Okay. Yep. Can anyone fill in this line here? So because our data is quite small, I'm just going to define it using 5 factors. Yep. Okay, cool. Oops. And now we can fit the model. Let's see how good is our model. It's pretty crap. Okay. Seems to be learning, but not particularly well. Yeah, so you can start seeing that our model is overfitting. So the loss function is okay for the training data, but it's pretty crappy for the validation data. And if you look at the validation data, so the mean square error of 1.9, so that means that on average, each rating is wrong by about 1.5. So it's not terrible, but it's still not great, right? So we can use this function to calculate the number of parameters, and Arun walked us through it before, how to calculate this number. Okay, so I'm just gonna skip through all of these. Okay, so if we go to this new Collab model, can someone explain what is happening in this step here? Why is the first layer has this dimension? Yep, Mario?
Yeah, it's putting the users and the items next to each, like concatenating them next to each other.
Yes, so correct. So if we look at the forward pass here, right? So we are looking up, we're doing that VLOOKUP again, that the vector for the user, and then the vector embedding vector for the item. And what we do in the next step is that we concatenate. So we put them next to each other. So now the dimension of that vector is the number of factors of the users plus the number of factors of the item. So that, in our case, that will be 28 plus 21. Based on fast AI documentation, can somebody explain what does this step do here? Get M size? Yeah, so I guess unless you caught this particular detail in the lesson, then you might not know. So basically, get M size gives you the recommended size of your embedding factors. So fast AI thinks that for your users, you should represent it by a vector of size 10. And for the hobbies, you should have a vector of size 9. So you can see that there's actually a lot of parameters for the amount of data that we have. So let's see if we have any more luck with this model. It seems to be slightly better than what we had before. So now we are going to, I think I'm just going to skip straight to this Collab Learner using a neural network. So that's basically exactly the same as this model here, right? So here we want to have 2 layers of 50 and 20 nodes. And you can see that that will be a massive number of parameters for our data. So I expect this model to massively overfit very quickly. Yep. So by printing our learn model, we can look under the hood, what's happening here. So we have the embedding matrices, and then we have a series of linear, layer, ReLU, and batch norm, and we can go into that in another lesson. So we have two of these groups, and then a linear output. So now the trick question is, can you explain why the number of parameters is 2,580? Yep. Can you type out the equation to give you that answer? Does anyone want to take a stab at this question? Okay, so maybe in the interest of time, I will walk through it. So Neil has got, okay, 19 times 50. Sorry, what's 19? 19, oh, okay, yep, so that's the first linear layer, right? But remember that the embeddings are also trainable parameters, right? So you need to consider these as well. Yeah, this is quite a tricky question. So I'm just going to type out the answer here. So for the user embedding matrix, you will have 28 times 10, right? Because it's just basically a square, right? Of 28 rows and 10 columns. For the hobby embedding matrix, you will have 21 times 9, right? For the batch norm layer, so as I explained in the note before, maybe I do not have it here. Okay. So for the batch norm layer, it has this number times 2 parameters, so it's 0 in this case. This layer has 19 times 50. And because the bias is false, so that's only 19 plus times 50. This layer has 0 parameters. This batch norm has 50 times 2. The next linear layer has 50 times 20. And then the second batch norm has 20 times 2. And the final linear layer, because it has a bias term, it will have 20 times 1 plus 1, right? So if you add up all of these things together, then you will get this answer here. So I'm just going to copy and paste this block of code to show you in a pretty table what that looks like. Yep, so it will explain, this block of code here will explain exactly how many parameters are in each layer. Yeah, so the last question is a hard question, and does anyone want to tackle this question? If we want to turn this regression task into a classification using the same Collab AI model, what changes do we have to make? So remember that a model has the training has 3 inputs, right? You need to consider the data, the output, the model, and the loss. So can anyone try, what do we need to change this problem into a classification problem? Yep, so Elliot said loss function from MSE to cost entropy. Yeah, that's correct. Yeah, this is the model here. Stephen said number of output layer to be range. Can you explain what you mean by that, Stephen? Stephen, can you explain your answer? I think I probably understand what you mean. So remember in this model here, right, it's outputting 1 number. But if we want to change this into a classification problem, then we need the output to be 5, right? Because we want to predict which class it is in, and there are 5 classes. What else do we need to change? Think about this, the output of the model here of the forward pass. What do we need to change about that? Yep, yes, Stephen is correct, and that's the same as my explanation. Yeah, so also you have to change the output to be the softmax function, right? So you need a softmax for the 5 probabilities, right? So that's the whole bunch of different things that you need to change to actually turn this into from a regression problem to a classification problem. Yeah. Softmax is included in the cost entropy, right? Does anyone want to take this question? I believe that it is not. It might be, but yeah, we just probably have to double check. Yeah. And what I have found, so actually I have run this by myself, and what do you predict about the training of this model? So remember what I said before about this being an ordinal regression problem. Do you think that treating it as a classification problem is going to work? Yeah, so if you implement this yourself, you realize that it doesn't train really well for exactly the reason that we said before. So if we treat this as a classification problem, it means that all the classes are independent from each other, and it means nothing, right? So if you classify cats or dogs or flowers, these categories don't have any meaning. But in our case, the ratings do have an order, from 1 to 5, and that's why simply treating this as a classification problem is not going to work really well. Yeah, so I hope that you have found that exercise useful. I'm going to post the completed exercise on the GitHub page, and you can go through it in your own time. Yep, so I'll pass it back to you, Michael, to wrap it up. Sorry, it took a bit more time than expected.
That is all right. Thank you, Gwen and Arun. That was awesome session, and really enjoyed the hobby sheet and doing some stuff on that, something a bit more practical, which is really cool. I hope everyone is doing really well on their group projects. I would definitely, hope that you guys are starting to get your ideas together for what you're going to present. I will aim to release some more information about what that sort of final week will look like this week, and the plan of attack is for you guys. So definitely make sure that you're working hard, and we will talk to you soon, and hopefully see a lot of you in person next week. Awesome. All right, guys, thanks for joining us. Have a great week, and may the force be with you, Leo.
See you, everyone.
See you guys. Have a good
Thank
week.
you.
Ciao.